Okay, my friends, this never gets old. They are still trying to figure out what's going inside of the nucleus of atoms. Extremely surprising nuclear physicists have a groundbreaking observation of strange matter. They come up with all these names. It's unbelievable. There is two particles that exist. All right, here's what they're saying. Their data was gathered by using experiments in Jefferson's continuous electron beam accelerator facility. Well, we have a pulsed laser beam electron accelerator facility. All right, this is our high-speed development facility. A pulsed red construction laser and two nails. They should be very, very close together. These are too far apart. But when you fire that in through that and hit right in between it, and if they're tight enough together, all you're going to get out is the white coming through. The black will go around. It's too big. They can't get through there. There's so much of a collision there, it pushes it around. And then with the selfie side of this, he took all the pictures. Rod Warren pretty much did this. He was trying to do the double slit experiment and just did it with one slit and made a Venturi, just accidentally, just playing around as a guy on the street. He didn't do it for any big purpose. And when I saw the things that he was putting up there, and people just sort of laughing at it, saying, oh, look at all these funny looking colored things. Well, I knew. I said, how did you do this? And he worked with me absolutely, and I will always be grateful. And this was the phone, a Galaxy S3. And that's it right there. I did the same stuff he did, but he, you know, you got to be you got to have some time to do this and do it right. And he did. And I show all of those different pictures of light, how they spin and how the particle goes and how you can speed them up and slow them down. You see these? This is obviously faster or slower than this, one or the other. And the same thing here. If you can't see that's accelerating, I don't know what to say. You know, and that are the Higgs fields. All of these things are now fully understood. Well, they have been, but they're refused to even be discussed. This is that white shower. You see this? Electron shower. This is Cherenkov radiation. This is not me. This is not my stuff. They say you come in, it comes in with a muon neutrino. The black ball never changes. You see, it stays the same coming in, and even when it crashes, and turns into Cherenkov radiation. It's well defined, never changes. The white one explodes into showers. If you can't see that, I can't say, I cannot help you. The black ones never even ever change size. They're exactly the same size. And they will snake right back in as quick as they can get to an area that is not concussed. That is so concussed, nobody can get in there. As opposed to this one, where some of them came through, along with the white. All right, this is a little wider, so we got a couple of really hits coming through, and some little black came through with it and created enough of a wave to you can see the black. And you see the white glowing. That shouldn't glow like that. They're normally not like that until you get that explosive action. Normally they're about like that. Pretty much the same as the black looking size. To me, I don't know. That's what I see. And again, I'm just an observer. I'm trying to understand what I see, and for me, this is the new model. That's it right there. Bohr and the standard model and all that stuff, forget about it. This is the new model, electron flood theory. And it's dipoles. It solves 100%. You show me anything, I can explain it using this model. Even the hurricanes and floods we're having now, and these tornadoes, these terrible violent outbreak of tornadoes, when you see all those hailstones coming down, there's an interaction of the black and the white particles in the air. And the black particles are the ones that are the killers. The white will burn things, but it won't break things up and slam them and destroy them like the muon. The muon is our tornado particle. Now, photons contain both of them, and they're bouncy. Now, this is wrong. 1839, I think it's wrong. I'm going now with 1823 dipoles, which are the electrons, make up a proton. And a proton, I believe, is shaped like this, where the black is in the center and the glowy particles are around the outside. That's what I'm seeing right at the moment. And nobody understands this stuff. Even Yale says nobody understands it. And he's right. And I applaud Professor Shankar for making that statement, right? Day one in the quantum physics. I took that course at Yale, quantum physics. And so, you know, he's a nice guy, but it's nonsense. He's just repeating what he was told to say. And he told the kids, that's all you have to do and you'll be okay. Wait a second, I'll show you this. And again, nice guy. This is the only one I found at Yale was just honest, to be perfectly honest with you. All right, this is out of control. This is the LHC, Large Hadron Collider. They wanted to use photons. Photons are the light particles, the light energy packets. Listen to this. They had a special meeting in 1978 to discuss the prospect of such collisions, which are physics' case for studying photons collisions. 1978. I was already up on these photons at that point. Down here it says something, it was first proposed to do this physics many years ago, but the project didn't materialize. Hold on one second. There's some more about this. All right, this is the crazy thing. Protons are literally big chunks of tiny particles, and they smash them together and they look at all these little particles and they seem to be all sort of different, but they're not. They're only different in the fact that some of them have more energy than other ones, and some of them have separated from the other ones. So now they're seeing this. They're calling them quarks and strange matters and semi-inclusive, deep inelastic scattering. They just have no idea what is inside of the nucleus at this point, none whatsoever. They're saying that these building blocks of protons, that's what I am showing you, the building blocks of protons, neutrons, electrons, everything is in there is nothing more than this little dipole. But they're saying the building blocks of protons, quarks, and gluons can sometimes march through the nucleus of an atom in pairs. They are almost always in pairs. They refer to them as diquarks. This is all new stuff. And I tried to work with the people at the Thomas Jefferson National Accelerator Lab, but I was called a fool. All right, so as I showed you, this is nothing more than light being crushed, showing these quadratic gauge coupling events, which are these right here. They're trying to understand this. And this is from 2020. And this is about the Higgs boson. I'm showing all of these things that they wanted to see. And it comes down here, where is it? Way down here. Here we go. These are the coupling events they want to look for. And here they are right here. It's just the particles coming in and hitting them and pushing all the other particles away. And different speeds cause different spins and different secondary interactions. And I'm sure the wider the venturi, the different, you see how it looks to me like their tighter venturi gives you this. You know, I think they have a sort of kind of understand what's going on, but not really. But this is light. This is light. All right, and they're trying to understand, and it's increased the hell out of the power of this light. Once it comes in and they interact with each other, as you can see, it is extremely violent, these interactions. Well, you can see it right here. As they come together, you got just nothing but whiteness, which is the electron neutrino. They come in black and white together, just doing their job, heading forward. Boom! Now the white one goes, and the black one just says, I never change, never gonna change. I just do what I do, and that's goes. And I think I have something here from Fermi Lab that shows it's called the point particle, which you know. Anyway, well, as a matter of fact, here it is. All right, this is it. This is from Fermi Lab. I didn't take that picture. These are the particles they have seen. They've seen them separated, and I think they see them together. They call them gluons. They just don't understand them because they're dealing with nothing but debris. We're watching them develop and then watching them split and then watching them come back together. It doesn't get any better than that. Here's what they're seeing. They come down, and then they dig through, and they see the really heavy-duty colored ones, the real sharp colored ones, taking off and never coming back. That's because they have enough energy to escape. The red ones are way out on the outside edges, and they're not being glued together tightly. These are inside, really, and when they go, they're gone. The red ones are out here, they're sort of hanging on, and they keep spinning around out there. They don't go flying forever. That's what the difference is between the frequencies. And I can show you that in our, well, I will show you in 1 second. But remember what I showed you here was the particles, the neutrino values, turning into photons, turning into sterile neutrino and a muon and a electron shower. And here's the green doing exactly the same thing. Comes through here spinning with the neutrino values, and then here's the green. Now here's the one where I said it's just getting ready to spin. You see it, the bottom one is the one that's getting glowy. It's getting glowier and glowier here. And it will spin to the back, and the top one will go to the front. So that'll become an upspin. Right now it's a downspin when they see them. That's the kind of thing they're talking about when they say spin this and that. There's only two particles that exist, the black one and the white one. Everything is made out of them. And that's exactly what it is. A proton is nothing more than this. It's not this with a bunch of little quarks and things and, you know, a couple little things floating around in here. It is nothing more than I think it's 1823 dipoles, and every dipole is a magnet, just like that. But when they're all together, they make a ball. Now, what happens in that ball? Where did the negatives go? Where did the positives go? Did they stay just like this, a ball on top of a ball on top of a ball, and they're like all bar magnets glued together? I do not think so. I think what's happening to them is this right here in the nucleus. Simple as this. All the black we know can separate from the white, and I'm showing it right here. I believe all the black is forced to the center, almost just like what they say is a proton, which is all the mass. And these are the white particles that are trying to get to that mass. The bigger the black hole in the center, the more white particles are going to try to get in. And there's going to be an equal number of attractions to what is held on out here. These are going to be just loosely held because they're trying to get in, but these guys are really trying to get in. And I think that's just what these are. It's just the negatives. They're not like dipoles here, 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 here. I think that's what it's appearing to me. Now, I could be wrong. I could be wrong. These could be this could be a dipole, dipole, dipole. All these could be dipoles as well, but I don't think so. There wouldn't be enough core attraction. It would be just too much floating around. And I've seen the Russians had this in 2015 or 2014, actually. Hold on, let me get it, hold on. Okay, this comes pretty close to proving what I'm saying. This was done in, I think, 2015, 2014. The Russians were in space, and they had in their space station a vacuum chamber. This is in a vacuum chamber. A vacuum chamber means you pull all the particles out. There's nothing in there that has any molecules in it. It's basically a vacuum of no particles. What they did then was they made a plasma. A plasma just means very, very, very fine dust particles with an extra charge to them. So they have an extra electron, basically. In my mind, they're having one extra charge that has to go somewhere, and nobody wants it. Nobody wants it. So when they injected this stuff into there, these are the white particles that are glowing. Now, I believe they're glowing because they're shining a light into here to try to see this. So the only thing that's going to glow back is the particles that the light they're shining in is hitting, which are these. the black hole here is it doesn't bounce back. The dark matter does not bounce anything back. It only absorbs. Now, well, no, it doesn't absorb. I'm sorry. It doesn't absorb. It doesn't reflect. It pushes. So what happens is it's just collecting around here. And the only thing that's lighting up is the particles here that we're bouncing into. So that's what these electrons are. I think they surround the core. That's my point being here. I think this is this. And the ones that are farther away, you see how they're tighter in here? That's the tight, that's the blue. And you get further way out here, you get to the red. There's no, they're just hanging around. Maybe they're going to be trying to get there, maybe not. Now this you can see is not really 100% round, so they still have some gravitational influence. But that is what I believe a black hole is. I believe this is dark matter, which is all the black parts pushed to the center, and all the glowy parts want to get in and get to it. And that's what creates mass. And as far as I'm concerned, the core of our Earth could absolutely be a black hole just like that. I see no reason to not suspect that. I see no reason to suspect that it is an iron floating fluid core. None. I know we have a magnetic field, but that magnetic field is a product of our ionosphere scrubbing all the particles in space, because the space is 100% saturated with these light particles. They're everywhere. Everywhere, and dust and so forth. That's why our ionosphere is like 2,700 degrees, something like that out there. Why would it be 2,000 degrees out there? Why? Everybody thinks it's freezing cold. Not at that layer. And that's the layer right now that's interacting with our global warming, causing a hell of a disturbance. Whether we all of a sudden getting impacted by more energetic, heavier particles, we're going through a soup, or it's just that our balloon has ballooned up so much from burning and all that business that we're scrubbing harder and harder. One way or the other, we're either getting bigger and scrubbing, or we're hitting something harder and scrubbing. That's the only two possibilities I can find. All right, you've seen all my particle showers I'm talking about and all these little diagrams. These are what's called Feynman diagrams. He's the guy that says, here's what happens. These particles come in. For some reason, we don't know what it is. These little squiggly lines mean fields cause other things to happen, and then we see these effects cascading down the line. Now, as again, I believe these are all a tighter venturi, a wider, I don't know what he's using here. I really don't. And I believe this is probably blue and into the really high range, because I can show you the blue ones spin like out of control spin. Well, here's the blue. Hold on. You see the blue compared to the rest of them? Blue is like phew, on steroids. You can't even tell there's two particles until it finally gets down to here, slows down enough where you can actually see it spread apart. There's actually two whites, like there is on all the other ones. There's two whites, one on the top, one on the bottom. But that one, the blue is spinning so fast, or it's moving so fast, it's crushed together so tightly, the white ones are on top of themselves. But there's two of them. You can finally see them down here. You almost can see them. I have another shot where you can actually see them. There's the tiniest separation. But that shows you light is spinning, or spinning one way or the other. Normally it's a right-hand spin. And that I can show you as well. Hold on. All right, this is what light does. It spins. It doesn't just go like this. It spins. And these are all, you see all these little spins? This is a drill bit going through that. Now, sometimes they go this way. Sometimes they come over and they go right through the center. Sometimes they go under and they come off this way and they come over here. That's why it sort of bleeds off to the side. These are what they call interference patterns. Or yeah, they think there's a wave here and a wave there, and they talk two slits. This is a single slit venturi. And that's what it's caused by, is the spinning particle. And as I showed you, the blue one is a spinner. Hold on. You see that? That's light spins. And the tighter it gets, in the tighter bunches, they make each other glow. They're forcing their fields against the other fields. And this, I'm not sure where that came from. I don't want to make any big statements about that, but it is light particles, and I believe it's coming at us, and I believe we're seeing the dark core coming. Well, you see what you see. I don't want to make any statements about that. That was not our work. Someone did send it to me and made some statements, but I won't repeat them because I cannot support them. This is that white showers coming through there. Remember I showed you electron showers? There they are. Virtually no black at all in there. And what is all this? Why are these big disks coming out of here? What are these? They call those Higgs fields. And what happens is when these white showers interact with dark particles. Now, whether these are dipoles and they're hitting them and they're making them spin like that, I think that may be the case. These are dipoles that are in the air, basically. Extra heat molecules, because you can have extra electrons in the air, which is heat. And it appears like they're hitting them and making them spin like crazy. And the red ones spin faster. This one is a blue, or almost blue, and it looks like it's being pinched. I have some other ones that are really, I have so much stuff, it's just fabulous. I was just excited for years doing this. I mean, I'm telling you. Every morning was like Christmas. And I will never, ever be able to thank Rod enough for all his hard work. Anyway. Okay, when I talk about going to all these courses, I go online. They're free. You can go to, I probably did this one, I can't remember now, MIT. This goes back to 2013. This is Professor Shankar. He's from Yale. And this one here is about the double slit experiment. It begins with a detailed view of the double slit experiment. Well, if we go up here and we just start right off at the beginning, all right, let's see, this is...
all right, so
whoops,
that's the spirit.
This is right here. Here's what he says. He's saying nobody understands physics.
The bad news is that it's a subject that's kind of hard to follow intuitively. And the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics.
He's the one that I showed you the diagrams, the quantum physics diagrams.
So in some sense the pressure is off for you guys because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
obviously he's kidding around. He's going to give them the best information he's got. But the best information he's got is based on nothing. Nobody understands it because it's just wrong. And he's man enough to stand up and say that. I applaud you, sir. All right, don't forget that Professor Shankar, who I do applaud, and I see him as a hero in science, although he didn't respond to me. But anyway, these are the Feynman diagrams. He's talking about Feynman doesn't even understand what he sees what they see, but they have no clue about it. No idea why it happens. Okay, so once again, Jefferson Laboratories, what they're doing is they're using electron beams. They're using a continuous electron beam accelerator, but what they're doing is hitting a nucleus and seeing what bounces off. So in the experiment, the nuclear physicists tracked what happened when electrons from this continuous beam scatter off the target nucleus. So they're not using photons crushing them, they're hitting a big heavy-duty thing, and they probe the confined quarks, wherever that means, inside the protons and neutrons. Well, protons and neutrons are nothing more than balls of little particles. Now, the results were recently published, So what is this? These studies help build the story to a motion picture. I showed you the motion picture of how a struck quark turns into hadrons. Well, they're just, now they call them neutrinos. I don't know what the hadrons, I don't care about talking about all these different names they throw out. W bosons, Z bosons, hadrons. In a new paper, we report first ever observations of such a study for the lambda baryon in the forward and backward fragmentation regions. In like a lambda, out like a pion. Remember this, in the forward and backward fragmentations. That's where they break up the particles. It's just what I showed you on 1,000,000 times. Here they are right here, coming through the venturi. In the forward and leaving edges, they're all broken up. That's all they're talking about. And you have to use light to do this correctly. You can see all this debris that they're seeing, but really they don't have the understanding of how it originally was configured and how it came apart and how it went back together and how the different energy levels. Let me show you green versus red. All right, you see these? This is nothing more than the green, only it's much more reactive than the red. And I can prove that. These are the same particles, as you can see. I think you can see them. They're the white ones and the blacks, same thing. Now this was from another guy we were working with, Fabian, and he did some really nice work. I don't know if what phone he had, but they're all working with CMOS, and they were saying, yeah, we can see all these cosmic rays. They're using these to do cosmic ray detection. All cosmic ray is a high energy particle, nothing more than that. It is as high energy as you want to get. Now here's the green and the red at the same time. See this? This is through the same venturi over here. You see how powerful the green is? See how weak the red is? Just pushed it out of the way. And then it kept going, and then it concussed way out here again. Same particles as the red. And this is what the red looks like when it comes through. It stacks up on itself, neutrino, photon, neutrino of what knows what. And then it just exploded into the sterile muon, which is the black ball, all by itself. And the whites just turn into the shower. Precisely what CERN and Fermi Lab and all of them, Jefferson, they all want to see this. And they can't do this. And I was rebuffed by virtually all of them and finally told, don't come back, stay away from us. We don't want to see you ever again. Because I have the information that makes their stuff not look so good. Sorry, that's just a fact. Okay, this is really amazing. They want to use the LHC as a photon collider back 50 years ago. All this is, these are photons coming in, smashing together and creating the showers that I show you right here. Whoops. These showers right here. They're coming in, and the reason they're creating showers here is because there's a venturi. That means there's like a slit right here, but it forces them together in this manner, not just a flat slit. It's a crusher. So all of these fields have to crush down, and when they do, they just explode. So we are actually separating the white particle from the black particle, and that, my friends, is undisputable. Here it is right here. And these are the same particles that Fermi Lab sees. They say the same thing, fixed, never changes, glowy edge, almost no mass whatsoever, but gets big and small, and that's what we show right here. The black one is the fixed one. It never changes, no matter what you do to it. These can get big and small. These get big when they're forcing themselves through particles that are in front of them, and they get small when they're behind. And that's what's called an up and a down quark, or whatever they want to call them. They got so many names now, it's amazing. But this is what they're talking about, this quadratic dipole. And they want to study them. I think I showed you that today. Yeah, quadratic gauge coupling. This is what this whole object thing was about. To enable CERN to study this type of coupling. But they were trying to use protons. They can't do that. Look at how big protons are. Look at this. Look, each bunch of protons containing 100 billion particles. When two bunches cross each other, they come this way, it'll smash. A few of the protons, about 25 out of the 100 billion, will collide. The rest, they just keep going. They just miss each other because they're not really hitting head on. They're sort of gliding off to the edges. Hitting head on is very hard to do. So we are forcing them to go together. And they can't get out of that squeeze. That's the squeeze zone. There is no escape. You see, here it is coming. Squeeze, 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 crush, boom. And there it is right here. That's the boom part. And they break apart. The black leaves the white, that's fission. It reattaches over on the other side of the venturi, which is fusion. In between, like I say, this is here and this is here. They're rounded actually. And the pinches here so tight that only the black, which can squinch down, I mean the white, can squinch right down, just like fluid. It just goes right through there. The black fixed, never changes. And they are they are always the same size everywhere you find them. And they will jump right back in at the edges. All the edges, you'll see them here. And there's a certain distance from the venturi where they start to reattach. But originally they were separate. I mean, they were attached together. This is the same particle as this one. It's just that this was colorized. And it's a red particle. And that's the same as they're seeing at all of them. CERN. Now, I went to University of Geneva. And I showed them all this stuff. They were as nice to me as anybody has been. They looked at it, but they didn't want to interact. But I see that, I know that they understand what's going on here. You can't possibly not understand it. It's just not, it's impossible to not understand. This is a pulsed red laser. Boom, 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 boom. This is the leading edge, which is a wave. You can see that, it's a wave. Well, I've also shown you it's a particle. Well, why is it a particle and a wave? Well, the particle is here in this black zone. And the white is in front of it, forcing itself through all the other whites, which push back. It's push to shove. You push me, I shove back. I'll get out of the way, but I'm going to fight you a little bit. And this gets glow and glow and glow. And then all of a sudden it has to accelerate. All right here. It's glowing, glowing, glowing. Now you see the wave stretching out. Well, the particle's still back here in the black spot. And the wave is just pushing faster and faster and faster. And then all of a sudden, it's pushing against itself. Bang, 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 bang. This is where neutrino flavors are developed. Different energy levels. Here it's an energy level. Here it's a different. Here we're getting more energetic, and extremely boom. And then you get this separation. And then you get this enormous subatomic nuclear explosion. That's what that is. That is exactly like an atomic bomb, but it's subatomic. You see these reverse waves out here? Let me turn off this light. Sometimes it makes it easier to see. You see those reverse concussion waves? That's literally the disaster zone from this nuclear explosion. And all of that is power. That's the key. This is power. Here it wasn't so powerful, going this way, until we interacted with the venturi. Now we got some power. Anytime you see radiance like that, that is energy. Energy is what we need to run cars and houses and lights and fight fires and pump water and do manufacturing. Right now we're destroying the Earth's environment. I mean, it's absolutely, well, I'm not even going to get into that. What I am seeing and you're seeing is light being accelerated, and it is light, it is photons, it is particles, it is muons and electron neutrinos. That's all there is, a black and white particle. I showed you that, and I can show that in spades all day long. Here they are. These are the photons. Now, how did they get to be photons? Well, they came flying out of a laser from over here. You see the black, and the black, and the black. These are the pulses. Now, the black and white is the two different particles. The muon neutrino is the black, the electron neutrino is the white. Normally they are opposites and they attract and they snap together like little bar magnets. As they start to build up against themselves, they get brighter and brighter and brighter and brighter, and then they, for some reason, I can't tell you exactly why, they form this as the dipoles, and they're one against the other. Now, the one that's leading, the white, will charge up and it will flip. That's the muon wobble, they call it. It spins. And then that one will come up front and it'll charge up and then it'll flip. You see back here, the white one's in front, it's getting charged up. It had already flipped by the time we see this one. I can show the green, and with identical particles, one of them in the phase of flipping. I'll show you that in a second. But all of these are neutrinos. They don't have the same energetic value as that or that or that, but they're also neutrinos. They're just not hitting in the same intensity. And these are that when they're just explodes. At the Venturi, they just turn white and black. That's a separation of powers. Now, anybody that can deny that, I can't imagine how it's possible. And when I say that the black pushes away, here it is right here. This is coming through, and there's a little bit of black coming through with the white on this one. The other one showed no black whatsoever. And here is the white concussing ahead of the black. The black doesn't grow, it stays the same size, it's just keep moving, guys. And they say, whoa, there's other guys in front of us. I said, well, push them out of the way. Yeah, but they're pushing back. Well, glow and push them. And they glow right up and they push them out of the way. That's what this is. These are concussion waves. And now follow me through on this one. I always assume everybody understands what things are, but a lot of people don't. What is a particle collider, a particle accelerator? Well, what is that all about? Well, here's the deal. Certain particle accelerators, they're called colliders. Some of them just accelerate, but they don't collide. These are colliders. They have particles that go around and around, and they smash head on. They're special machines, smash atoms into pieces. Well, what are atoms? Protons, neutrons, electrons. All right. They use charged particles like protons and electrons, and they spin them around, 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 and then they get smashed together. They use electricity to push them. Electricity, my friend, is light. Light is atomic vapor. This is from my papers back in 1968, 70, in that area. I was in the Army in nuclear, Nike Hercules missiles, and when I got out, I went into physics, and I quickly left because they just couldn't take the reality that nothing they were saying was right. Nothing they were saying was right. Everything had to be a dipole. I mean, I had it all done, and this was my statement back from that time. Transfer of energy is from light to atomic vapor. Light makes dipoles, and they're always dipoles. I had all this down. I mean, I did it. This is not something I just did in 15 minutes. I spent a lot of time. I was very, very dedicated to this, and they just really basically destroyed me. No interest whatsoever. Now, this is 1970, 71. I got out of the Army in 1970. And I went right into this, and that was it. I got out in about 2 years because it was just nonsense. And it still is. Now, wait till I show you something. It goes back to 1978. This was 6 years before 1978. Listen to this. Okay, this goes way, way, way back. Like I say, this is long, 50 years ago almost. And this was, I was apparently showing that you could remove the negative particle from the positive particle through some device back. I don't remember this. I got to be perfectly honest with you. When I saw it, I said, holy smokes. Because this was all experimentation, different, oil drop experiment and all the different laws and so forth. And here's all the different laws. And right here, photon is the packet of light energy. I mean, this is the first thing I wrote. And this is what we're talking about today. There it is right there. All right, this is from 2020, and this is all about the same particles I'm talking about. And this is what they're talking about is new physics beyond the standard model, BSM, beyond the standard model. And they're trying to figure it out at the Large Hadron Collider. But they can only, until they start working through the Venturi, they're done. You have to crush these fields. Head on, they don't hit head on well. Head on, they can skirt off of each other very easily. Through the Venturi, there's no escape. All right, through the Venturi, this is what you end up with coming out of there, just raw white electrons. There is no escape. All right, the black ones can't get through, so they have to go around. So we know they split. And this is absolutely physics way beyond the standard model right here. Acceleration of light, explanation of the particle nature of it and the neutrino values, the flavors they call them, energetic flavors, fission and fusion, using this as our laboratory right there. That's our laboratory. I couldn't cost half of what they're spending at CERN.